following program is brought to you by Caltech.
Our final speaker this evening is Dr. Mark Swain of JPL. He received his bachelor's degree in physics from the University of Virginia and his PhD in physics and astronomy from the University of Rochester. Mark is going to discuss how all of these exoplanets are categorized and characterized.
Well, thank you. It's my pleasure to finish up 3 great talks by telling you a little bit about how we are characterizing these new and exciting worlds that people are finding. Now, characterization isn't always an easy business, and certainly the reason I get up in the morning to do this job is really to connect to this question, which you've heard about from the previous speakers, and that's, are we alone? This question is timeless. Humankind has been wondering about our place in the cosmos for almost as long as we've been able to express ourselves. And this question is ageless. It connects to people of all ages, and this is my son's attempt to connect this question in the same way that the Bronze Age folks in central Germany were wondering about their place in the cosmos 3,000 years ago. Now, I'm going to focus on molecules. In this characterization of exoplanets, molecules have a unique role, and that is because we can't send a spacecraft to probe exoplanets the way we can visit planets in our own solar system. So we're going to have to do something else to really learn about the properties of those atmospheres. And we can use molecules that we detect in those atmospheres as a proxy for probes, and those molecules are going to do a job for us. They're going to help us figure out what the conditions, the composition, and the chemistry are of those atmospheres. Molecules also have a role in establishing, when we do get to that stage where we are characterizing a habitable planet in detail, molecules are going to be the possible precursors of biotic activity and maybe even those biomarkers, that decisive indicator that life is present and active on a planet. Now, I've got a little movie to show you how we do this molecular spectroscopy in exoplanets today. This process really started with the Hubble Space Telescope, and so in our movie, here we see the Earth, and the Hubble Space Telescope will be coming into view soon. The first detection with Hubble of an atom in an exoplanet atmosphere was made about 10 years ago, and since then we've moved to studying molecules as well. We've added that to the list. Now we've taken Hubble and we're pointing it at a star that hosts one of these transiting planets. Here you see the planet. It's orbiting the star. Now we know exactly when the light is going to dim, because in this case the star has been previously characterized by maybe a Kepler or one of those other types of transit surveys you've heard described tonight. So again, we know exactly when we're going to look, and we're going to use the fact that the light from the star is dimming and that the planet's either coming in front of the star or going behind the star. We're going to use that to our advantage when we make this measurement. In this video, we're going to focus on what's called the secondary eclipse, when the planet goes behind the star. And so right before the planet goes behind the star, we're going to turn on our instrument, and we're going to start taking measurements. First, we get the star plus planet, and then as the planet goes behind the star, we're just going to measure the stellar component. Here we go. Then the planet comes back out, and we get star plus planet again. Now, if our instrument is a spectrograph, and we use one of those prisms that you heard about to break light into its colors, we can measure this depth at every single wavelength. If we do a very precise job of making this measurement, we could just take the difference of the star plus planet and the star portions of the curve. And when we do that, we can make a spectrum. This is just how much light we have, and this is color or wavelength. And this is real data combined from several different instruments. That data has wiggles in it. Those wiggles are the imprint of molecules. Molecules have specific wavelengths or colors that they absorb or emit light in, and those make those wiggles in the spectrum. So we can use those wiggles to figure out not only what molecules are present, but how much of them there are. Now, to date, we've detected water, methane, carbon dioxide, and also now CO, carbon monoxide, in exoplanet atmospheres, and that's been done in several planets. So once again, right here, you've got the whole story of how we do this. Today it's done with transiting planets. We take the difference, we get the spectrum, and we use the wiggles to infer what molecules are present and how much of them. So the first spectroscopic detection of a molecule in an exoplanet atmosphere was this data right here. The black points are the data set. Those measurements were taken with a Hubble Space Telescope, and they were measurements of a hot Jupiter planet atmosphere during a primary eclipse. So the planet's in front of the star, and that starlight is filtering through the planet's atmosphere. And this dip you see here and here is absorption due to, in this case, a combination of water and methane, which is causing the feature right here, in that planet's atmosphere. Now, this was a little bit unexpected. The atmosphere in these hot Jupiters is well, it's hot. They're quite close to the parent star. This one has a 2-day orbit. So if you imagine Jupiter, bringing it into a 2-day orbit around a sun-like star, that atmosphere is just being blasted by very intense radiation. And we actually expected to see carbon monoxide there. So this was a bit of a surprise. Now, that measurement was shortly followed up by a beautiful measurement taken with the Spitzer Space Telescope at longer wavelengths, working further in the infrared. And that spectrum shows the presence of water. The second spectrum comes from when the planet goes behind the star. So this is, now you've seen a spectrum from in front of and behind the star. Those two measurements can be combined, and this is something that's unique to the transiting planets. They can be combined to give you some knowledge of what's going on in the atmosphere in different places on that star. I'm sorry, on the different places on the planet. The primary eclipse transmission spectrum is probing that terminator region, that junction between day and night, while the secondary eclipse spectrum, when the planet goes behind the star, is probing the day side. So it is possible to start trying to infer how the properties of that atmosphere change between the intensely irradiated day side and the night side. Now, we don't have a night side spectrum yet, but we're about halfway around, and this is an area of active research. Now, something else to keep in mind about these spectra is that when we measure them, a lot of work goes into that measurement, but when you're finished with that, all you have is really a wiggly line, and we have to do something to figure out what molecules are present based on those wiggles, those fingerprints. That's done by building a computer model of the planet's atmosphere, and in that computer model, we adjust the temperature and the molecules that are present and how much of them. And this gives you a sense of some of the effects of those adjustments. This blue line is a model of this planet's atmosphere with just water, and you can see we don't match the data there, and we don't match the data there. But if you add methane to the model, you see it does a much better job of replicating the data. And if you add a little bit of CO2, it does an even better job. So this modeling process is an absolutely integral part of interpreting the measurements that we make with a spectrograph. Now, something that's kind of exciting that's happened relatively recently is that we've moved to start to do some of these characterization and this measurements of molecules and atoms in the atmospheres of exoplanets, we've started to do this from the ground. This is significant because there are a lot more ground-based telescopes than there are space-based telescopes. Now, from a ground-based telescope, you're struggling with the Earth's atmosphere, but 3 different teams at this point have found ways to do a very detailed calibration and remove the effects of the Earth's atmosphere. And that's really going to open up this discovery space. And I think that in the very few, 2, 3, 4 years going forward, we're going to see a lot more results like this. I want to highlight just one of them to show some of the unexpected things that we're finding. This is a day-side emission spectrum from, again, the day side of one of these hot Jupiters. It's a multi-instrument data set. We have some Spitzer, some Hubble, some ground right here. This gray line is the model that people expected. And you see there's this great big spike that was found using the IRTF, this little telescope right there. That is probably some sort of fluorescence feature going on in that planet's atmosphere. Detailed explanation is still in the process. So this is just an example of some of the new and exciting things and unexpected things that we've been finding. Now, transiting planets have been a great source of targets for characterization, and in the future, with the right sort of instruments, perhaps a specialized, very high-precision space mission, we should also be able to do non-transiting planets. Now, I have this little Lego model. Yeah, by the way, the first movie you saw was built by the JPL pros. A guy named Tom Momery did a brilliant job on that. This, I'm sorry to say, was done by me, but I had a lot of fun. And you can, by the way, if you like building with Legos, go to the Kepler website. They've got the instructions for this. Okay, so the noise you hear is the gear train. The gears in a Lego set are, they make a lot of noise. Anyway, we've got a solar system here, and let's focus on our gas giant. We're viewing the system from the transiting configuration. Now, if we take our spacecraft and we fly up to the non-transiting configuration, and we imagine measuring how much light that system's putting out, we see we get the bright side and the dark side, and then we'll get the bright side. So if we keep measuring, we'll see that system get brighter and dimmer. In fact, this has been done with Spitzer using photometry, and so hopefully in the future we'll be able to extend these sort of techniques to spectroscopy. Now I'm going to finish by highlighting some of the I'll take it it's, I guess Che's a keeper, right? I'm going to finish up by just highlighting some of the really surprising things we've learned from methane. In our own solar system, there's a saying that's, if you want to find life, follow the water. What we're finding with methane in extrasolar planets is that there are all sorts of unexpected things. And so if you really want to understand exoplanets or the details of their atmospheres today, right now the story is follow the methane. Now maybe 10 years in the future it'll be a different molecule, but methane is the star of the show today. It's really been revolutionizing our view of exoplanets, in part because it's a standard diagnostic. Every time that we take a spectrum of an exoplanet where we see molecular signatures, guess what turns up? Methane. Methane has revealed a large diversity of conditions within these hot Jupiter atmospheres. These atmospheres being hot, there's an expectation of carbon monoxide being the dominant carbon-bearing species. Sometimes we get a lot of methane, sometimes we get less methane. We still don't know why. Methane is what revealed that unexpected emission mechanism I showed you, this fluorescence. And we still don't know exactly how that's working or what the details of that process are. Methane is also revealing some complex chemistry must be responsible for these composition differences. We still don't know. And finally, the latest result, which is there's a controversy around this methane detection in a warm Neptune with 2 different teams having different analyses of the data. But the fact that people are talking about methane in a warm Neptune is just an indication of how far we've moved in 2 years, 3 years now, from the hot Jupiters to a planet that's a stepping stone on our way to what we really want to do, which is looking at molecules that may have biological significance on worlds that are similar to Earth. And I'll end with that and leave you with the thought that we're making good progress on our connection to what is our role in the cosmos, and are we alone? Thank you.
This program is brought to you by Caltech. Visit us at caltech.edu.